So Newton's second law is directly, related here to a couple things that that we've looked at. The net force on a body is proportional to that body's acceleration in the same direction as that acceleration. So, you have a force, net force to the right. Which way is it going to accelerate? It's going to accelerate to the right. If you double force, right, 2 times the force, what are you going to get? Twice the acceleration. Now that's assuming the same amount of mass, right? Now, if you get a ton of mass, let's say you double the mass, but you have the same amount of force, what's going to happen? You're going to have half the acceleration. Or you triple mass, it'll be a third of the acceleration. And so the more inertia you have, the more mass you have, with the same amount of force, the less acceleration you're going to have. That's like trying to push a toy car versus a real car, right? You push that real car, and with a certain amount of force, you push the toy car. The toy car has lots less mass, a lot less inertia. It's going to accelerate much more rapidly with the same amount of force. All right, so for this one, we're going to take a look at some forces on a person in an elevator. And so we've got the person in the elevator standing, and we want to find out what is the apparent weight when the elevator accelerates upward at 2 meters per second squared, and then part B, when the elevator is moving at constant velocity. So first thing, go ahead and draw your free body diagram. Secondly, go ahead and set up the coordinate axis. What's positive, what's negative. 3, you want to set the sum of the forces in the x, sum of the forces in the y. 4, put your variables in there. And then 5, solve. Okay. So go ahead and pause the clip and do that and give it a try for A and B. And when you're ready to check, you can hit play to continue. All right, so for part A, the biggest thing to recognize here with the free body diagram and the elevator's motion, the elevator is going up and it's accelerating upward. It's accelerating upward at 2 meters per second squared. Therefore, the acceleration is positive. And yeah, it's going to be accelerating up, and we get 1,003. So that's what we would feel accelerating upward. Going into constant velocity, what's the acceleration? Acceleration is 0. So the weight, the apparent weight, is going to equal the actual weight, mg. And so we have 833, and we've got that. All right, how about when the elevator begins to slow towards the top floor at 2 meters per second squared? So this is again, normal force going up, which is the apparent weight, force of gravity down, and it's going upwards and it's slowing. So go ahead and set up a free body, or we'll set up some of the forces here. Again, positive up and then negative down, and then your variables, and then yeah, go ahead and solve for the apparent weight when the elevator is going to the top and slowing. So be careful there with your signs. All right, so let's see how you did. We should get, for part C, 663, the key with this one is recognizing as the elevator is going up, it is slowing, so therefore the acceleration is downward. And the acceleration is, as it goes up, it's slowing, and therefore the acceleration is -2. And so that's the key with that one there. All right, so why don't you go ahead and practice this one. This is a fish hanging from a scale, and we want to get A, B, and C at rest, moving upward and slowing at 3.2, moving downward and speeding up. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so for part A, it's at rest, so the force applied going up, you could have called it tension, could have called it a spring. Probably wouldn't technically be right to call it a normal force because it's not resting on anything. Unless it is resting on a scale, like a flat scale or something. So 49 newtons. B and C, it turns out, right, with B, it's moving upwards and slowing. Moving upwards and slowing. So, it's going up and slowing, therefore the acceleration is pointed downwards. But if it's going down and speeding up, right, acceleration is also downwards. It's speeding up and in the downward direction. So the acceleration for both are negative. So for both B and C, we should get 33 newtons as the apparent weight. All right, so here we've got 2 blocks, a 4-kilogram block and a 6-kilogram block, all connected through a pull system here, the force supply coming out to the right, and then there's a line of tension between them. Question is, what is the line of tension between them, and what is the acceleration of this system? And so what I did in class is I gave them a pause to try to figure it out on their own. So if you know what to do, and try to think through that, go ahead and pause the clip and give it a try. And when you're ready to check, you can hit play to continue. All right, so the big hint here is you've got to have these masses together, and you treat them as one object when you're trying to figure out this force. So we know the mass. We know we're looking for we know the force is 10 newtons. So we can find the acceleration, F equals ma. The mass is 10. The acceleration is 10. So the force, the force is 10, mass is 10, and then we're looking for the acceleration, divide both sides by 10. So the acceleration is 1 meters per second squared. That's the acceleration of both of these objects. And so we just treated them as one object. Part 2 is finding the tension. What is the tension here? So go ahead and pause the clip and give that a try. If you needed help with this first part, and then you can hit play when you're ready to check. All right, so we should get 4 newtons. We know that this is accelerating at 1 meters per second squared, and we have the mass, which is 4 kilograms. We know the acceleration, so it's going to take 4 newtons. So this is 4 newtons here. This is 10 newtons here, pulling the whole thing, but this one is just pulling this, right? So the tension is less there. All right, so why don't we go ahead and give this one a try, and let's see how we do based on that last one. You can try to set this up again, a frictionless surface. Go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so we're pushing the boxes with 7.5 newtons of force. We treat them as one object, so that's the very first thing we do up here. We treat them as one object. We have the force, and so we can find the acceleration of the system, which is 0.7979 meters per second squared. So all 3 boxes are accelerating at that rate. The toughest part of this question is figuring out right here, what is the force in between 2 and 3 here? Well, what you got to do is you got to treat 2 and 3 as one object, because right here, this is having to accelerate both these boxes. So mass 1 and mass 2 together are 4.5 kilograms. We know the acceleration, therefore we can find the force. And so the force between those right here at this spot is 3.591 newtons. And then finally, the final box, what's the force, right here at the final spot? It's only being, there's only one mass being pushed. We have the acceleration, and we can get how much force, and it takes 1.037 newtons to push that. All right, so let's go ahead and give this one a try. This is a mass here, or 2 boxes here, where, this is an all form IB question. Go ahead and read through the whole thing. Go ahead and answer what you think it is, and when you're ready to check, you can hit play to continue. All right, so one of the key things here is it says it's a rough table, and as it's being pushed, both boxes move at a constant speed, which is different. So, and it's asking what's going on with Q here. Well, if we draw the forces on Q, the box P is pushing on this indirectly, so you get the force applied here. But it says it's going at a constant speed. That means that friction is going back, and if it's a constant speed, we set up the sum of the forces in the x equals ma, and the x positive force applied plus the negative force of friction equals 0. So what's the force applied equal to? Friction. And so therefore, there is no net force. So the resultant force is 0. And even though there is a force on it by P, there's an equal and opposite force by the force of friction. So the net force or resultant force is 0.